Hello, and welcome to Ants Are Everywhere. We're taking a look at liburing, which is a library for helping you work with U-ring, which sounds like a birth control implant, but is actually a Linux kernel thing, a system call, for making it faster to work with async file operations. This was a fan request. You can make a fan request by joining our Discord channel, and the requests go basically to people who donate to the channel to make it better. And that's how they're scheduled. In this case, I don't know anything at all about U-ring or IO U-ring, other than I've seen it a few times in the past few weeks. Seems like people are into it. Seems like it makes the fileys faster and faster. And we'll see what it's about. It seems to be headed up by Meta. This guy, Jens Axbo, and this is his repo, and this is a library of helpers. I don't know if the request was intentionally to point to this library, or if they were intending to point to the main U-ring implementation. But this is what we are going to do, and we'll see how it goes. Let's read a little bit about it so that we at least have a starting point. So it says we have two circular buffers. We've seen circular buffers a few times, I think mainly in audio applications, but we will look at them. They are also called queue rings to track the submission and completion of IO requests. So we're going to make a bunch of IO requests. They're going to go into some queues, some ringed or circular cubes, some queues that are topologically S1. For storage devices, these are called submission queue and completion queue. And we've seen, I feel like we've seen a similar pattern. There was a completion queue, at least, probably also a submission queue in gRPC way back in the day. Keeping these buffers shared between the kernel and application helps to boost I/O performance by eliminating the need to issue extra and expensive system calls to copy these buffers between the two. So sounds like there's some shared memory. I don't know if that's the main source of the efficiency. According to the IO U-ring design paper, the SQ buffer is writable only by consumer applications, and the CQ buffer is writable only by the kernel. Okay, so only the kernel can say that a request has been completed. That's the C in CQ, and only the applications, I guess, can submit something. I don't know what this means, only consumer applications. I assume this means, so what's excluded? I assume that among the things that are excluded are user applications that are not the consumer applications, but I doubt you can exclude the kernel. And then it says eBPF can be combined with IO U-ring. And then here's some history. They've had async IO since version 2.5, which is many years ago, I think. I don't really remember where we are now. But it was difficult to use and inefficient, and only supported certain niche use cases. So I guess everything else is synchronous IO. Notably, it only prevents asynchronous operation, or rather enables asynchronous operation when using the O-direct flag. And while accessing already allocated files, this prevents utilizing the page cache while also exposing the application to complex O-direct semantics. And it also did not support sockets, so it can't be used to multiplex network and disk I/O. And it's exposed a significant attack surface, which makes sense because it sounds like we're sharing a bunch of queues between user space and kernel space. And Google's security team reported that 60% of the exploits submitted to their bug bounty program in 2022 were exploits of the IO U-ring vulnerabilities. As a result, IO U-ring was disabled for apps in Android. So it sounds like to me, as a former insider, currently outsider, that this is kind of consistent with what I think of development practices at Meta versus Google. Google is often very security focused, very security forward, and Meta, at least formally, was move fast and break things. And when I was reading this thing to you just now, my first thought was, well, it seems like we're sharing a bunch of stuff between kernel and the user space. Is that going to be a security problem? And it seems like it is. And maybe Meta is just like, we need to go fast. we need fast I/O because we're slurping all your data and sending it through secret loopholes. So let's look at it. I mean, why not? Let's take a look at circular buffers. They should basically just from memory be a buffer that you have some pointer that kind of wraps around. And they're used a lot in audio because of sampling, I think if I remember correctly. And, you have some slot that you're going to sample with, whatever. I don't know what a reasonable size is, but like, let's say 2 seconds of audio or 30 seconds of audio or whatever. And if you, and we're just going to overwrite data. And if you lost that bit of audio, there's nothing really you can do because it wouldn't have made sense to include it anyway, because the time of that part of music or that part of the conversation has passed. My water smells suspiciously like cat mouth. I wonder if my cat's tried to steal my water. Okay, so a circular buffer or a circular queue or cyclic buffer or ring buffer is a data structure that uses a fixed size buffer as if it were connected end to end. So this is just basically, I assume, a topological trick. Like if you ever played the Pac-Man. Pac-Man topologically is a torus in the sense that if you go off this end of the screen, you end up here. So these two are connected, kind of, which makes a cylinder. And if you go, I thought you could go off the top and come up in the bottom, but maybe I'm just misremembering it. Maybe it's just on a cylinder. At any rate, it wraps around, at least in this direction. And a circular buffer does the same. So it's topologically a ring, although in reality it's laid out as a line like in Pac-Man. A circular buffer first starts out empty and has a set length. In the audio case, it'll be the sample rate, I think essentially the sample rate or some function of the sample rate. And then in the IO ring, IOU ring, I don't know what the length is, it's some Q length. And we're going to write 1 in the center. Then we write a bunch more elements. And if 2 are removed, the oldest 2 values inside the circular buffer will be removed. They use FIFO, first in, first out. And so we're going to remove, I guess, 1 and 2. That leaves 3. And then if the buffer has 7 elements, because this is a 7-element buffer, it's completely full. And I guess we're going to overwrite data. We're going to overwrite the oldest data by looping back to the front. And so here are some useful properties. It does not need to have its elements shuffled around when it is consumed. If a non-circular buffer were used, then it would be necessary to shift all the elements. Yeah. So instead, we're just going to keep a pointer, and the pointer is going to wrap around. Maybe just using modular arithmetic, maybe using something fancier. And it's a good implementation strategy for a queue that has a fixed maximum size. Should be a maximum size. It's completely ideal implementation. All queue operations are constant time. However, expanding the circular buffer requires shifting memory, which is comparatively costly. Okay. So it seems like a standard thing for queues, although typically we don't see, I feel like I don't see a ton of queues implemented that way in most cases. For example, people often implement queues as Python lists or something similar. All right, so now with that, we're going to hop into the liburing code, and we're probably not going to see the implementation of uring, but we might see some examples like how to use it. And I don't really know what to expect. We're going to make some requests and get some stuff back. Actually, now that I'm saying this, let's see if we can pull up the API. Lord of the IOU ring. Blah, 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 blah. So here's the here's a mental model. There are 2 ring buffers, one for submission, which we saw SQ, and one for completion. They're shared. We saw that. That's in Wikipedia. You tell IOU ring what you need to get done, read or write a file, accept client connections, etc., which you describe as part of the submission queue entry, which is SQE. So we'll see that somewhere, I'm sure. And add it to the tail of the submission ring buffer. The tail makes it sound like there's a list structure, but I don't know. But you're going to basically add it to the ring buffer, wherever there is currently space. And then you tell the kernel via IO ring enter, which is a system call, that you've added an SQE to the submission queue. And you can also add multiple SQEs before making this call. And then also, IOU ring enter can wait for a number of requests before it returns. So the kernel processes requests submitted and adds completion queue events to the tail of the completion queue ring buffer. So that implementation sounds pretty simple. It's going to basically do, I assume what to it is relatively standard IO operations, and when you ask it for some bytes or whatever from a file, it's going to tell the completion queue when they are ready, and presumably have some sort of pointer to where they are, or maybe just add them to the completion queue itself. And then you read CQEs off the head of the completion queue ring buffer. There is one CQE corresponding to each SQE, and it contains the status of that particular request. Okay, that's really simple. Here's this low-level IU ring interface. And then here's some stuff about performance. And I'm just going to not really read it. Something about copying bytes. I just want to see some calls. Here is this seems to be an implementation of IOU ring SQE. So the submission queue entry, the thing that you add to the submission queue. I don't know if this is actually the literal implementation or if it's just a simplified one for this blog post. Might as well add the blog post to the Read It Later app as well. So you've got some opcode for the SQE, and opcode is presumably just a encoding of a fixed number of things that you can do, like read, write, etc. You've got some flags for configurability. IO prio, I assume, is priority. FD has to be file descriptor, yeah. And then we have some union of either an offset into the file or an address. And then we have an address, which is a pointer to a buffer or IO vex. I don't know what IO vex is, maybe like IO vectors. And we also have a length, which is either the buffer size or the number of IO vex. And then we have a union of some different flags. I guess different things you can do. I don't know if these are mutually exclusive. The union would suggest they are, but maybe there's some way to combine them. And then we have some user data. The data to be passed back at completion. This is a U64. I'm not sure how that's going to work. Maybe that's the amount of data you want. And then we have some other substruct, or rather a union of a struct and a U64. The U64 is pad, and then we can also have like personality or whatever. And then here are the opcodes. Do not perform any IO. Read V, write V. I'm guessing these are vectors. Vectored read, vector write. Let's look up IO vec while we're here. Describes a region of memory. Okay, great. Now I feel like I am situated. All right, so should we look at examples? We kind of just did look at examples. IOU ring, CP, proxy, poll bench, busy poll server, K digest. Maybe not. These look like some of them are mainly testing like edge cases. It may not be the most, well, these are examples, not tests, right? And these are examples, I guess, of the library and not of the raw implementation. I'm not, it's hard to say. There's real code here, but I don't know if it's what I want to look at right now. So let's look at source. I don't know why everything's so big. Oh, first of all, I'm zoomed in 200%. I don't know. Did I do something with my font here? I maybe made my font too small somehow. Okay, so here's source. What do we have? We've got a queue. And again, this should be a queue in liburing and not a queue in IOUring. We also have set up syscall. Version.c is probably just going to print some version stuff. Did we look at register? No. Let's look at sanitize, register. These are most of these are C files, but some of them are header files. I guess we should look at lib. Whatever a .map is, I don't know what that file format is. Let's just open all of them. There's just like 12 files here. We do have includes, which includes the liburing header, and a barrier, an IOUring header, and a sanitize header. Okay, so let's look at those as well. And then Arch should be like architecture specific stuff. Let's look at x86, just for fun. And it just has things like, what is the page size on this architecture? What was that, lib or syscall? That was lib, right? In here, in syscall, we have some stuff about registers, syscall registers. I don't really know what this is about. I'm guessing that maybe syscalls have are architecture specific in how they are implemented in some way. So for example, do syscall 6 has 6 arguments and is, I guess, using the EAX register and is doing this. We're going to push some stuff and do a syscall. So that this seems to just be it doesn't seem to be specific to URing. It may be something in general about syscalls. I don't know. So let's jump to the end here where my headers are. I don't think I want to begin with sanitize. Let's begin with IOUring.h. So I wonder if, this does seem to be the implementation. Maybe I'm wrong about that, but this, we do have an IOUring SQE struct, which I would have thought would be in the kernel implementation. But who knows? Certainly not me. And what is this? These are the flags. Length is the buffer size or number of IOVX. Yeah, this is basically the same thing we saw. And what? We have opt_val. That's not so important. And some command. If the ring is initialized with IORing setup SQE 128, then this field is used for 80 bytes of arbitrary command data. Okie doke. What else do we have? This is some comment. If SQE file index is set to this opcodes, to this 4 opcodes that instantiate a new file descriptor, like open@2 accept, then IOUring will allocate an available direct descriptor instead of having the application pass one in. Whatever. Okay, so here's some flags. SQE flags bit. And we have fixed file flag, IO drain bit, hard link async buffer select bit. And we have some SQE flags. Fixed file. This is the same thing. These are just defining, I guess, these enums as these bitty things. And we have like this IO SQE async means always go async. IO SQE buffer select means select buffer from SQE buff group. And maybe buff group is just a list of like reusable buffers. I don't know how you're supposed to select them. Maybe you select the next one or something. And this is don't post CQE if request succeeded. Skip success. So like this is like, I guess I'm going to fire something off and I don't want to know. Want to know what the result is. Here's some more setup flags. IO ring setup, IPOL, SQ poll, etc., etc. So these are like the context is poll thread. I don't know if this is a reference to the thread. SQ thread CPU is valid. App define CQ size. Attach existing WQ. Start with ring disabled and continue submit on error. Setup submit all says continue submit on error. So I don't know what sort of errors we're ignoring, but this is like a forced push onto the queue. It sounds like. I see. How do things look on the on your setup here? I know that like Samsung phones, at least, you can plug in, I think, a monitor to them, and they like expose like a desktop interface, but I've never used it. Okay, so I'm not sure really what all these flags do. These are maybe just too down in the weeds for where I am currently with this IOU ring stuff. We have some timeout flags, etc., etc. Let's kind of move on from this header. We can always come back to it. And what other headers do we have? We have a barrier from the kernel documentation, file refcount versus automatic.rst. A release memory ordering guarantees that all prior loads and stores, all PO earlier instructions, I don't know what PO earlier means, on the same CPU are completed before the operation. It also guarantees that all PO earlier stores on the same CPU and all propagated stores from other CPUs must propagate to all other CPUs before the release operation, a cumulative property. This is implemented using cfunc SMP store release. An acquire memory ordering guarantees that all post loads and stores, all PO later instructions on the same CPU are completed after the acquire operation. It also guarantees that all PO later stores on the same CPU must propagate to all other CPUs after the acquire operation executes. This is implemented using SMP acquire after control dep. So this is saying something about the behavior of releasing and acquiring. When you release something, I don't know what PO earlier is, but maybe program order. It sounds like when you call release, all the things you said before should already essentially be guaranteed to have happened. There shouldn't be a reordering that changes the semantics of release. And similarly with acquire, it's kind of how I will interpret that. So BK Rana says they don't understand English. I see. Well, welcome. You're welcome even if you don't understand English. That will make it difficult to talk. I'll wave, but I'm glad you're here. Okay, so these look like guarantees about the barrier, and then I don't know what they're actually implementing, but we have this thing like IO SMP store release. IOU ring SMP store release, and we're going to call standard atomic store explicit with a reinterpret cast and something about memory order release. So this is seems like a relatively thin wrapper around like barrier semantics in the Linux kernel, and it's not really sure if there's anything else going on here. But I'm going to look at this string. This appears in the functions, but doesn't it seem to appear in the functions we're calling? So I'm not sure how that works. I don't know if there's any relationship between the decision to name these, like SMP store release, and them actually having these semantics. I assume that I don't think there's any sort of automatic conversion. Maybe they're just making sure that these behave the way that they're expected for some API. and we're just going to ignore it. Liburing.h, which is different from what was it? iouring.h. And this is many lines of code. And I'm not sure what to make of it. iouring CQE iter init. So something about an iterator, I assume. Let's see if we can find the some of these major structs. Here's a library interface to iouring. We have iouring SQ, which would be submission queue. And we have a bunch of pointers. I don't know what K is as a prefix, but we have K head, K tail, head and tail, a ring mask, deprecated. Use ring mask instead of K ring mask. And also K ring entries. We're going to use ring entries instead. We also have K flags, K dropped, and array. And then we have this struct, which is the iouring SQE struct, which we have seen before. So the queue just has a bunch of SQEs. And I think that the queue is essentially mainly the list of SQEs. It doesn't look very ring-like yet. It just looks like a pointer to some SQEs. Then we have the SQE head and tail. And I'm not sure how they differ from the K head and the K tail. And then we have the ring pointer, which is, I assume, the thing that's going to wrap around. And we have our ring mask and ring entries and some pad. So again, I don't know what K is. K dropped. This might be like if you try to add stuff and there's no room. I guess that we are going to maybe drop requests instead of overwriting, potentially. I'm not sure. Or maybe that's configurable. And then we have iouring CQ. This is going to be the completion queue. Again, we have K head and K tail, and the deprecated K ring masks and K ring entries, and K flags, and also K overflow. And maybe we're not going to throw away stuff that's completed. I don't really know what the overflows, not overthrow. I don't really know what the overflow, how it's going to be implemented, but we can maybe see what's there. And we have a ring siz, I'm assuming size, it's size T, and a ring pointer, and then mask and ring entries and some pad. And then the IOU ring, it has the two queues, some flags, a ring file descriptor, and some whatever features, some unsigned features, probably some collection of flags, an enter ring FD. I don't know what enter ring is, and some more flags and some pad stuff. And then we have an IOU ring Z Crux Recur. RX and RQ is maybe request. I'm not really sure what that is. ZCRX. Should we look up ZCRX? Zero copy RX. RX is like receive. Okay. So this is some zero copy, I assume receive queue or something along the lines. We have some comment that says library interface. And we can do things like take a U-ring pointer, convert it to a U64, which is just going to do a cast, it looks like. And get probe ring. Return allocated IOU ring probe structure, or null if probe fails. I don't know what probing is in this context. Maybe we're probing for the free space. Freeze a probe allocated through IOU ring get probe, or IOU ring get probe ring. Yeah, I'm not sure what that is. This is something to check if an opcode is supported. It's just going to look, I guess, at the opcodes we have. We can init memory, init parameters, init a bunch of stuff. Some memory mapping, something about don't fork, and so on. Register buffers. This is kind of like setup in operations, I guess, with the two rings. IO wait. Enable or disable waiting. Setting of IO wait by the kernel. And this is some helper for peak wait single CQE function. Exported because of that, but probably shouldn't be used directly in an application. Okay, this is IO uring for each CQE. This looks like just some for loop helper function that we're just going to iterate, kind of like a for each CQE thing. Okay, so this is looking good. Let's look up IO uring probe. Probing supported capabilities. Translate this page. No. It prints if an operation is supported or not. Okay, so this maybe is supporting for, this is like maybe probing for what is supported in your version of IO uring or whatever. Okay, so this is interesting, but I think I've gotten what I want to get out of it. Here's sanitize.h. We can sanitize the ring, sanitize the region. I don't know really what we are sanitizing. I think I have opened up sanitize.c somewhere. Perhaps we will see it. Here's some FFI thing. And it seems to just be setting up, I assume, some FFI, but maybe in Clang. So we are possibly using Clang. If we don't have Clang, we're just going to include liburing.h. And I don't know what that, I don't know what that has to do with FFI. That just seems to be an include. But if we do have Clang, we've got this diagnostic stuff. I don't know. I don't know what this FFI is doing. It seems to be a mystery. Here's another header. I just opened all the headers. Not all of them are going to be great. This is some int flag thing. This is presumably integer flags. Whatever, like reg ring, register ring, regular ring, and then CQ enter. This is some enum. I don't know what this is being used for. Maybe this is like recording what we are doing. Like, do we issue some log or event when we enter, or we change one of these? I'm not sure. Ring enter flags. Okay, something about entering the ring. Here's lib.h. And my eyes noticed macro hot and cold, so we'll look at those in a second. And there's not much here as a header wise. So hot is just to mark something with the attribute hot, and similarly as maybe unused. I don't know if that's like unused as a return or what. And then we have some allocator stuff like uring malloc, which I don't think I've seen where that would be. Let's see if we can find uring malloc. Did I not spell it right? I'm not signed in. I don't know why. But I guess I'm not going to do that right now. Okay, and then here's the map. I don't know what a map is. FFI map. So we've got this seems to be some like dictionary essentially. And these things I assume are globals. Uring get SQE. These are a lot of the methods. Maybe like the API. Blah blah blah. Global. Is this just a thing for exporting documentation? A symbol table used by the kernel. A symbol table is a lookup between symbol names and their addresses in memory. That's system.map. Maybe this is understanding map files. Is this the same? The symbol map in address and order format. This is, I think, a different thing. I'm wondering if this map file is used for a similar purpose. A standard text file format for describing Linux software. It also refers to the database constructed from these files. So what do we have? We have copying policy, original site, platforms, keywords. Are any of these similar? These do have like version numbers. Let's put the global keyword. Small objects global. I'm guessing it's related to one of these. I don't really know which one or what, but that's fine. Again, this is another map file. We will just plow along. Here's lib.h, which I think we just looked at. Did we not? Or maybe this is source lib.h as opposed to include lib.h. And no, I think we looked at this. Right, we've got the maybe unused, hot, cold. Okay. And that brings us to the actual implementations. Although, what about setup and syscall? So setup.h has some stuff for initializing parameters, umap, rings, IOU ring, mmap, etc. So IOU ring mmap. I guess this is for setup maybe because it's for setting up the queue, but it's going to take a file descriptor, some parameters, which is a struct, and some and the SQ, which is a struct, and the completion queue. And I guess using the parameters and the two queues and the file descriptor, it's going to create the IOU ring struct and allocate memory for it, I assume, without even looking at the implementation. But what else could it be? Okay, so now we have syscall.h. Let's look at that. And it's small. We're just going to include the right syscall header for the architecture. Fine. Then where does that leave us? We have q.c, sanitize.c, and register.c. And how big are they? 423 lines of code, 160 lines of code, and 420. Nice. So let's get sanitized. That should be quick. And so if we want to sanitize SQE address, we pass in the SQE thingamajig. And then we call asan address is poisoned. I think this is only on Clang, right? I'm not sure. And we pass in the SQE address, which is, I assume, just some pointer. And if it is poisoned, we're going to call asan describe address. And then we're going to call exit 1. And that's error, right? I think I use it all the time, but I'm blanking. Hello. I don't know why. Did I not send this? I thought I sent that. Clumsy make. What's going on? I don't know. We're looking at this IOU ring thing. I don't know anything about it. Yeah, so exit 1 is failure, unsuccessful. Just wanted to check that before I said something wrong. Okay, so sanitize opt. The same thing is happening in all of these. We're just gonna this is just some interface to pass in the SQE struct as a whole, and the struct knows all of the interior pointers, and we're just going to call these sanitize functions on the pointers. And sanitize no op is going to do nothing. And then we've got this initialize sanitize handler. And I think that these things are maybe the opcodes. And then so it's like setting up, I guess, for each opcode, which sanitizer do we call? For example, IO ring EP poll wait. If we want to sanitize, I guess we're going to look at the SQE address. And then we have a bunch of other convenience methods. Let's see if ASAN is only available on the Autistic Self-Advocacy Network. Only available on Clang. Oh, it's a Google thing. No, it's part of LLVM and GCC. Okay, so it isn't GCC. I don't know if Google actually made it, or what. At any rate, okay, so it is in GCC. It's not just Clang. I was confused about why we weren't checking for Clang there, but we were elsewhere. That leaves us with register and queue. So let's look quickly at register. What does it mean to register a buffer, for example? IO ring register buffers update tag. We're going to give it the ring, an offset, I assume, some IO vex, and whatever tags are, and an unsigned NR. I don't know what that is. And we're going to sanitize the IO vex. And we're going to call, we're not going to call. We're going to create a struct of type IOU ring R source update 2. It's going to be some update struct with some offsets, some IO vex, some tags, and whatever an NR is. And then we're going to call do register, passing in the IO ring register buffers update flag with the update, which I assume is basically just going to be like a patch in the ring. And this function with this flag is presumably going to know how to take this information and like atomically update the thingamajig with it. Do we get to see the do register? Do register is inline. And we're going to sanitize the address. And if we're going to AND the flags with reg ring, in which case we're going to set the opcode to or equals the IO ring register use registered ring. And we're going to set the file descriptor to the enter ring file descriptor. Otherwise, we're going to set the file descriptor to the ring file descriptor. Again, I still don't know what enter ring is. And then we're going to call sys IO u ring register. And that's maybe going to send it off to the kernel to do something. I can't use GitHub search because for some reason I got signed out. But maybe Google will find this function. A bunch of issues. Whatever. Okay, we'll plow along then. It's called sys. I assume it's sending it off to the kernel or something. Okay, so here's q.c. And this may be the main thing. I see IOU ring get CQE. You're going to give it the ring. And a pointer to a CQE pointer. Or I guess a pointer to a list of CQEs. And some data. And what's it going to do? We're going to set loot to false and error to 0, indicating that we haven't made an error yet. We'll set need enter to false, and we're going to get the ring enter flags, and whatever NR is, whether we have NR available. Maybe we can look this up. look up NR and enter. But I really want to have NR. Update NR number. Number is NR is just a number. It's just an abbreviation for number. And then initiate and or complete asynchronous IO. Okay, so right. We did see what IO uring enter was, because that's the thing that that's like the syscall that tells the kernel to actually enter the uring. I'm just looking at source code, clumsy matrix. I don't know what these message retracted are, but let me know if you have further questions. We're just looking at source code right now. We sometimes build things, but not today. Okay, back to the queue. So, blah, blah, blah. So the enter command, which I had forgotten about, but we saw earlier in our exploration, is just going to tell the kernel that we've manipulated the queue and it needs to kick off its stuff. It needs to do its thing. So, where was that? Okay, so this is like flags, I guess, for when we do enter. We're just grabbing them, I assume. And then we've got this IO uring peak CQE. So we're going to look at, assume the CQEs on there without removing them. Check for errors. And if we don't have CQE and the data wait number is non-zero, I guess, and the data submit is non-zero, if we already looped once, we already entered the kernel, since there's nothing to submit or wait for, don't keep retrying. So if it is zero, right? Because wait number will be true for anything that's non-zero. Okay, I was just misreading that. Okay, so if these two are zero, so if we've looped, we're just going to break. Otherwise, we'll say need enter is true. And then if we have the wait number is bigger than the number we have available, or we need to enter, then we are going to set, we are ORing. So I think we're unsetting the get events flags and the data get flags and set need enter to true. And if we need to enter, we'll set need enter to true. And if we don't need to enter, we'll break. And if we've looped and data has TS, whatever data has TS, whatever TS is, then we're going to do this get event stuff. And if we're down here, I think this is where we actually enter. We're going to call IO uring enter 2, passing in the enter ring file descriptor, which is, I guess, something we pass to the kernel on enter, and whatever with data submit. I assume that the kernel is going to fill this data out. I'm not sure. And the wait number, and some flags, and some data args, and some data size. Let's see if we can look up this syscall. I'm assuming it's not usually prefixed with a sys, although maybe it is. IO uring enter 2. Okay. Unsigned to submit. What is to submit? FD is the file descriptor returned by IO uring setup. Okay. To submit specifies the number of IOs to submit from the submission queue. Okay, so we may not be submitting the whole submission queue at once, and so data submit, I guess, is like how many of the requests do we want to submit at this time? And then we're going to, I guess we get something back. That's presumably the number of things that successfully were fired off. And then we're going to subtract them from the amount that needs to be submit. It returns the number of IOs successfully consumed. Okay, so that is actually pretty straightforward once we decode all of the lingo. Here we have IOU get CQE. What were we just looking at? Get data. No, that we were looking at underscore IOU ring get CQE. Without the underscore, it's just like, I guess we're like setting up data and then calling the internal version. We have get events, which I assume is going to be similar. We can peek at the batch CQE and so on. And I imagine everything else is going to be more or less the same. Is there anything that we really want to see? So it looks like this library is mainly about manipulating the data that you need for the system calls and then making them correctly. So there's not, I guess in that sense, there's not like a lot to it. Although without it, you maybe would have a hard time doing things correctly. But I think that's about all that we are going to see. There should be a corresponding thing for like submitting SQEs. I don't really know where the data returned is. That should be a fact about the CQE data structure. Let's see if we can find that. So SQEs should be the submission requests, right? CQEs should be the completion thingies. Where are you? The completion queue is part of a CQE, but where is this defined? Maybe here? Okay, the kernel process request submitted and adds completion queue events. Right, so they are completion queue events. And then you read the CQEs off the head of the completion queue ring buffer. There is one CQE corresponding to each SQE and it contains the status of that particular request. And then, but how do you get the data? Okay, let's just ask the AIs. Let's ask, what, ChatGPT? In IOU ring, if you have a CQE, where is the actual data from the, each, for example, file read? Is it contained or pointed to by the CQE? And if so, in which field? It is not contained in the CQE itself. Instead, the data from read or read v operation is placed into a user provided buffer. Okay, so we, I think we did see when you pass the SQE in that you pass in a buffer and that just buffer gets filled. So I guess it's your responsibility to know where that buffer is. And with that, I think we've seen what we came to see. I hope you enjoyed exploring the source code with me, and I'll see you again soon. Thanks for joining me.